Welcome back to the course of micro engineering. A very good morning to all. As discussed with our previous lecture, we are going towards the end of module number 5 today by covering the remaining types of measurement. In today's lecture, we are going to see the measurement procedure for the antenna gain and the measurement of noise which gets generated during the microwave operation. So in today's tutorial or lecture, we will see the measurement procedure of unknown gain of the given antenna, and then we will continue with the last microwave parameter measurement, that is the measurement of a noise. Measurement of a noise we will see in the form of calculated, or it is quantified in the form of noise temperature and noise power. So in today's lecture, let us start with the measurement procedure of a typical antenna gain and how it is obtained. Now I will give the heading over here as antenna gain measurement or measurement of antenna gain. Measurement of antenna gain. Okay. Say the gain of the antenna is a very important parameter which is measured in the microwave system in order to provide or in order to calculate the different types of losses and the different amounts of transmitter and received power required in order to set up the wireless communication. So gain of the antenna is a very important parameter, and the gain of the antenna is dependent on radiation characteristics of the antenna, right? So there are three basic methods with which the gain of the antenna can be measured. So there are distinctly three different process or separate operations procedures available in microwave technique through which we can measure the gain of the unknown given antenna. So the methods are, so I will list out the methods of measurement. Methods of gain measurement. There is no single technique, but there are multiple techniques available in order to measure the gain of the given antenna. Gain of antenna. So the first method is, we call it as a standard comparison method. Standard comparison. In this method, what we are going to do is, we are going to compare the gain of our given test antenna with the gain of the standard antenna, and we are going to calculate the unknown gain of our test antenna. There is a second method, we call this method as a two antenna method, in which we are going to make use of two identical antennas. And the third method is very accurate, in which we involve to make use of three separate antennas. Three antenna method. So all these methods we are going to see one by one in a brief way. Okay. So the measurement of the antenna gain can be calculated using either one of these techniques. But out of these techniques, the three antenna method is the most accurate one, because it involves making use of three separate antennas, and it will improve the accuracy of calculation or the computing operation of the gain of the test antenna, right? So in a standard comparison method, so first of all we will discuss a standard mechanism, standard method. We call it as a standard comparison method. It is straightforward. So in standard comparison method, what we do is, we will take an antenna whose gain is already known to us, okay, and that antenna we treat it as a standard antenna, okay, and we will establish a relationship between our test antenna whose gain we want to measure, okay. Now this test antenna whose gain we want to measure is used in a receiving mode, okay. So here a block diagram is this is our standard antenna system. Okay, I will denote just a block diagram, right? So this is a standard antenna. This standard antenna is used as a transmitter. I will write here as a transmitter. The gain of this transmitting antenna is known to us. This is known. So here the gain of the standard antenna is known, and the power with which we excite this standard antenna is also known to us. So what we do next is we will place our test antenna or the prototype antenna whose gain we want to measure at suitable distance such that it will come in the far field radiation zone of the standard antenna. So what we do over here is we will place our test antenna as a receiving mode over here. Okay, so this is a receiver antenna, and the antenna whose gain we want to calculate is called as a test antenna. So this is a test antenna. Okay, so here we want to calculate the gain of this particular antenna. Okay, and the distance or spacing between these two antenna is, let us say, capital R. Now this capital R satisfies the condition of far field, right? So I will write over here, this is located in the far field distance. Okay, so after making this type of arrangement, we will start the operation. We will feed the known amount of power to the standard antenna, and the standard antenna will radiate. The radiations of standard antenna are received by the test antenna, which is kept in the far field radiation zone of the standard antenna. Okay, and here at the end terminal we are going to measure the received power. Okay, and the received power, the transmitted power, and the gain of the standard antenna with the gain of the test antenna, they are interlinked with a certain equation, standard equation, where the gain of the receiving antenna is directly written in dB in comparison method. So the gain of the receiver antenna is equal to gain of the standard antenna. I will write it as a GS, or rather I will make use of the convention of the same values of GR and GT. Okay, so GR, that is a gain of the receiving antenna, in dB is given by GT, that is a gain of the transmitting antenna in dB, right, plus 10 log to the base 10, because we are dealing with a decibel scale, right, into bracket we will write received power PR divided by transmitted power PT. Okay, so here only the unknown in this case is the left hand side. So this we want to calculate, that is the gain of test antenna. Okay, on the right hand side if you see, the gain of the standard antenna is known, right, and we know what is the transmitted power, that is PT. Okay, and we want to measure the received power. Once we know the power received by the receiving antenna, we can put the values into this particular equation and we can calculate the value of the gain of the antenna which we want to test. Okay, so this is a simple, straightforward a procedure of standard comparison method. Okay, so let us go ahead and see what is the two antenna gain method. So here I will start writing two antenna gain method. So here usually the test antenna whose gain we want to measure is used as a transmitter as well as receiver, right? So here please remember, in this particular method the signal is transmitted from the transmitting antenna with certain value of a gain GT, and the signal is received by the test antenna again with the same identical one whose gain is say GR. So here I will draw a simple block diagram. The test antenna whose gain we want to measure is used as a transmitter. So this is our test antenna. Okay. And we will place a receiver in the far field zone approximately, and at the receiver we also make use of the same test antenna, identical test antenna. Okay, so what is the difference between the standard comparison method and two antenna method? In two antenna method, the prototype antenna which we are using is the same antenna, that is a test antenna. The same antenna is used at the transmitter and the same antenna is used at the receiver. Okay, it is made sure that the test antenna and receiver antenna are separated with large distance so that they will fulfill the condition of far field radiation, right? So whenever the signal radiated by transmitter antenna, it will be received by the receiver antenna, which is placed in the far field zone. Okay, so the transmitter antenna is excited with certain power PT. Okay, the gain of the transmitting antenna is GT, right? Now similarly, the received power at the receiver is say PR. Okay, the gain of the receiving antenna is say GR. Okay, now here if the frequency of operation is known to us, then the received power in this particular case, remember here that the transmit antenna and receiver antenna are identical. So here I will write the TX and RX test antennas need to be exactly identical. Then only the calculation of gain is going to be a correct value. Okay, so the received power, right, at receiver antenna, so how it is given? It is a standard equation of the received power at the receiving antenna. Received power PR is equal to the transmitted power multiplied by the gain of the transmitting antenna, right, into lambda square, where lambda is the operating wavelength, divided by 4 pi r whole square. Okay, so here multiplied by GR. So here this is a particular equation in order to calculate the received power at the receiving antenna. Okay, so here we know what is the transmit power. Okay, we don't know what is the gain of the transmitting antenna and what is the gain of the receiving antenna, because both antennas are identical. Operating wavelength that we know, because we know with what frequency the antennas are excited, and we also know the separation distance between these two antennas. Now this equation can be written in terms of decibel scale, that is, we can write this equation as the gain of the receiver antenna in dB, right, plus the gain of transmitting antenna in dB, right. So this can be given as 20 log to the base 10, right, 4 pi r upon lambda, where lambda is the operating wavelength, okay, plus 10 log to the base 10 of received power PR divided by transmitted power PT. So here we are going to make use of this particular equation. Say if you compare on the right hand side, the R value is known to us, that is the separation distance. Okay, so the lambda value is known to us, that is the operating frequency. We can convert that into operating wavelength. Okay, so we should measure what is the received power, that is PR, and we already know with what power the transmitter antenna is excited. So all these four parameter on the right hand side of this equation is known. Okay, so here in this particular case, if we make use of the same antenna. Okay, so here the condition is if identical antennas are used, if identical antennas are used, then what we can write? If the identical antennas are used, then gain of the receiving antenna is equal to gain of the transmitting antenna. So the above equation will become 2 times gain of the receiving antenna, or we can also write this as a 2 times gain of the transmitting antenna is equal to 20 log to the base 10, okay, 4 pi r upon lambda plus 10 log to the base 10 of received power divided by transmitted power. Okay, or we can write this as gr is equal to gt provided identical antennas, right? So this can be written as 1 by 2 20 log of 4 pi r upon lambda plus 10 log to the base 10 of ratio of received power to the transmitted power. Okay, so here if we make use of identical antennas both at the transmitter and receiver, by using this particular equation we can calculate the unknown gain, and this particular method we call it as a two antenna gain method, right? And we will proceed further with the another technique which is commonly employed and very popular in the measurement of gain of the unknown antenna, because it makes use of not only one or two, but it makes use of 3 different antennas. Okay, and this method is very accurate because in the second method, two antenna method, unless and until the two antennas are exactly identical, whatever value of gain that we calculate is not going to be accurate unless and until the two antennas are exactly identical. Okay, so in order to come over this problem of two antenna gain method, we will provide or we will develop another technique. We call it as a 3 antenna gain method. So the same I will discuss now. So 3 antenna gain method. Three antenna gain method. Now let us see what is this 3 antenna gain method. The name itself indicates that we are going to make use of 3 separate antennas. They are not supposed to be identical, but they are supposed to be different from each other. Okay, so in the 3 antenna gain method, the dislimitation or the disadvantage of making use of a 2 antenna gain method can be come over. The 3 antenna method is most general method in order to find the gain of the all 3 antennas. Remember, in this particular method, the gain of the all 3 antennas which we are going to make use in this operation can be calculated. Any 2 antennas are used at a time. Okay, so in this particular technique of measurement of gain, though we are using 3 separate antennas, at a time we are making use of a 2 antennas, right? For example, if we have 3 antenna system in this way, let us say this is antenna 1, let us call it as antenna 1. The gain of this antenna 1 is say G1. Okay, similarly we have the second antenna. Okay, so this is say antenna 2. The gain of this antenna let us denote by G2. Okay, and let us say there is another antenna, third antenna, which is different again over here. Let us say this is an antenna 3, and this antenna again will have certain other value of a gain, let us say G3. Now here our aim is to find out gain of all these 3 individual antennas. So how this can be made possible? at a time two antennas are being used. For example, we can make use of antenna number 1 and antenna number 2, or we can make use of antenna number 2 and 3, or we can make use of antenna number 3 and antenna number 1. Okay, and then we will establish the simultaneous equation which is represented in the form of gain of any two given antennas. Okay, so the simultaneous equations, how we can develop, by taking into account the gains of any two antennas at a time. So this can be written as, let us say, the power transmitted by antenna number 1 is say PT1, right? Similarly, the power transmitted by antenna 2 is say PT2, and similarly the power transmitted by antenna 3 say PT3. These could be different powers. Now similarly, these antennas are going to receive certain power, and this received power could be from the cumulative summation from all these different types of antennas, and PR1 is say received power by antenna number 1. Similarly, PR2 is say received power by antenna number 2, and similarly PR3 is say received power from antenna number 3. Okay, then if we know the transmitted powers, if we measured the received powers at these three different antennas, then we can establish a relationship, right? So at the time, please remember, we are making use of a two antennas, and while making use of two antennas, we will separate the antennas such that they will get located in the far field region of each other, and the distance between them is capital R. Okay, so then we can establish a relationship between the gain equations. Okay, so gain of the first antenna, so here I will write the gain of the first antenna G1 in dB plus gain of the second antenna, let us call it as a G2 in dB. How it is given? This is given as 20 log to the base 10. Okay, so 4 pi r upon lambda. Remember that all these antennas we are operating at the same frequency, that means the lambda is going to remain same, right? Plus 10 log to the base 10. Now we are taking antenna number 1 and antenna number 2. Okay, so let us say we are going to measure power received by antenna number 2 with respect to power transmitted by antenna number 1, PT1, right? So this is the first equation. Similarly, if we consider antenna number 2 and antenna number 3, then we can write this equation as gain of the second antenna in dB G2 plus gain of the third antenna G3 in dB, right? So this is equal to 20 log to the base 10, right? We are replacing the first antenna with the third antenna. We are keeping the second antenna same at the same distance, 4 pi r upon lambda. Okay, now here we are going to take the different ratio of power. Now here the receiving antenna is the third antenna, so I will write it as a PR3 divided by transmitter antenna is the second antenna, PT2. Okay, and similarly when we make use of antenna number 1 and antenna number 3, then we can write this equation, gain of the third antenna in dB plus gain of the first antenna in dB. Okay, so this can be written as 20 log to the base 10 4 pi r divided by lambda, right, plus 10 log to the base 10 of, right? Now antenna number 1 is receiving while antenna number 3 is transmitting. If you look into the first equation, the first antenna is transmitting. In second equation, the second antenna is transmitting, and in third equation, the third antenna is transmitting. Similarly, if we look into the equation number 1, the second antenna is receiving. In second equation, the third antenna is receiving, and in third equation the first antenna is receiving. Okay, so here the capital distance r and lambda is known. Okay, and we are going to measure the power received at all these three antennas, and we already know what power we made use in order to transmit via these three different antennas. So the ratios of power in these equations are known, the value of separation distance is known, and the operating wavelength is also known. So for all these equations the right hand sides are known. Okay, so what we get three equations, g1 plus g2 with certain value x, call this an equation number 1. Similarly we get g2 plus g3, we will get certain value y, call this as an equation number 2. And similarly g3 plus g1 will get certain value z. Now here we have three equations with three unknowns on the left hand side. So the unknowns are g1, g2 and g3. So we have a set of three equations with three unknowns. Now we can solve these three equations simultaneously. So here I write solve above three equations simultaneously. To evaluate or to compute gain of first antenna, gain of second antenna and gain of third antenna. So this three antenna method is very helpful and which facilitates us to calculate gain of all the three different antennas using this particular measurement technique. So this is all about the different types of measurement methods of the gain of the unknown antenna. So the first method is very simple and straightforward. We need to simply compare the gain of the test antenna with the standard available antenna. In the second method, we call it as a two antenna method. We should make use of exactly identical antennas at the transmitter and receiver, right? And in the third method, which is mostly accurate method, which involves making use of three separate antennas. They are not supposed to be identical. Okay, so this three antenna method is very popular and it is popularly being used in the microwave applications wherein we want to measure the gain of the antennas. And this particular method provides us the gain of all the different antennas which are used in the operation. So this is all about the antenna gain measurement in the microwave system. Let us go ahead and see the procedure of how to quantify the amount of noise in the microwave circuit, right? So the next is microwave noise measurement. Okay, so what is the noise? Actually, the noise in the microwave circuit, it is the representation of random behavior of the charge carrier inside the circuit. Okay, so the noise is basically, so I will here write, noise is characterized by random process of charge carriers within the given system. So we can say that inherently in any particular microwave communication system, the presence of noise is inherent, because the noise is getting generated as a random process of the charge carrier which are there inside a given particular system. Okay, or when they propagate from one place to another place. Okay, now this noise can be added from the external sources also. So the noise I will write over here. The noise is present inherently inside a system, and it is also contributed by external systems. Or sources. Okay, so the noise can be generated inherently. It is always present inside a given microwave system, and this noise is contributed again separately by external connected devices or by external systems, right? So the noise can be passed in a microwave system from the external sources, and it is also getting generated in the system itself. The noise of the microwave circuit is effectively measured in terms of a noise temperature, and sometimes a noise figure is also used. Okay, so here noise is generally measured in terms of noise temperature, right? Or sometimes the noise is quantified by noise figure, right? So a unit in order to calculate the noise is the noise temperature, or sometimes we make use of the measurement of noise figure in order to quantify the amount of noise present in the circuit, right? So the measurement of noise temperature. So how the noise temperature is measured? Noise temperature. So how a noise temperature is measured? So a noise temperature is measured by calculating the equivalent value of this temperature in a given component by the measurement of the output power when the circuit is terminated with a matched load at 0 degree Kelvin, right? So here I will show you the arrangement of the measurement of the noise in terms of noise temperature for a given particular system. Let us say this is a system, or we can call it as a device under test, DUT, or system whose noise we want to measure. Okay, so this is let us say typically this particular system is an amplifier system whose noise we want to calculate. Now this device is connected to a power meter. We are going to measure a power. So that's why this device under test whose noise we want to quantify is connected to a power meter, and this device is terminated on the left hand side with certain load. Let us say this is a resistive load. This is a measurement procedure. First load has certain resistance R, and second certain resistance R2. Now both these loads are at a different temperature. Okay, so let us say this load is at temperature T1, which is greater than the temperature T2 of the load. So this is a load 1, it is a resistive load, and this is a second load. Okay, this is also a resistive load. So these resistive loads having the resistances R1 and R2, and these loads are at different temperature. Let us say T1 is greater than T2. So that means first load is at high temperature and second load at low temperature. So in order to calculate the amount of noise which will get generated when the device under test is connected to these two different loads, we are going to measure with the help of a power meter. Okay, so what we do over here, this type of arrangement we are going to make use of in order to quantify the effect of produced noise in the device under test. And typically the device under test is going to be an amplifier circuit in general. Okay, so this device under test is connected with a power meter at the output, and this device under test is connected with the two separate loads at its input. These two separate loads are being operated at different different temperatures. Okay, so that one load is operating at higher temperature in comparison with the second load. Okay, so the amplifier or the device under test whose noise we want to measure in terms of noise temperature is connected to one of the two matched loads at different temperature, and the output power is measured for the each case. Okay, so if the T1 is the temperature of the load number 1 and T2 is the temperature of load number 2, okay, then we are going to measure the two different powers. Okay, so here first we connect the device under test to load number 1. The load number 1 is at higher temperature T1. Now we are going to measure power in the power meter. Let us call this power is Pn1. Now this power is when load 1 is connected, right? Then we measure this power and we denote this power by Pn1. Then what we do is this same device under test, now we will connect to load number 2. Now load number 2 is at different temperature. The temperature of load number 2 is lesser than temperature of load number 1. Again we are going to note down the separate power, and let us call this noise power sensed by the power meter is Pn2 when load 2 is connected. Okay, now in these two particular situation, the noise is getting generated within the amplifier itself, as well as the noise is getting contributed by these two different loads in different situation. Now we will establish a relationship of noise power with the noise temperature. Okay, so if the noise power measured in the first time is say Pn1 when the load number 1 is connected, then this can be given as the gain of the device under test K T1 into B. So this is external noise. This is external noise, right? We can say contribution from load 1 plus inherently the noise is present in the amplifier itself, so this can be written as a G K T E B. Okay, where TE is the effective temperature, and this component is inherent internal noise of device under test. Okay, now similarly when we measure the second power when the device under test is connected to load number 2, we can write Pn2 as the noise that is being contributed because of the external load at temperature T2 B. Okay, now this component of the noise power is the external noise contributed from load number 2 plus the internal noise, that is G K T E into B. that is going to be same. Okay, so this is inherent internal noise, inherent internal noise of device under test. So if you look on these two equations, Pn1 and Pn2, there is a common term in between these two equations, and the common term is the inherently present internal noise of the device under test. We are interested to calculate this noise temperature Te. This noise temperature Te is the noise temperature which is inherently present in the system or the device under test itself. Okay, so we have calculated what is the value of noise power Pn1 and Pn2. Okay, so if we take the ratio of these two equations, okay, so if we take the ratio of Pn1 to Pn2, this ratio of noise power we denote as capital Y, and this capital Y we call it as a Y factor. Okay, so if I take the ratio of noise power, we call it as a Y factor, and this particular measurement technique of the noise factor method, right? So here on the right hand side of these two equations, one common term is always present, that is inherently presented noise, right? So if we take this particular ratio, then we can calculate the internally present noise by making use of this Y factor. So here Te is internal noise temperature of device under test. So how this can be written in terms of these two powers? These two powers can be written as in terms of T1 and in terms of T2. Okay, so the noise temperature T1 and T2, there has to be certain relation. So this internal temperature we can write as Pn1 by Pn2 is equal to Y. We call it as a Y factor. So this can be written as Gk T1b plus Gk Teb divided by, okay, so divided by Pn2 is Gk T2b plus Gk Teb. So from the numerator we can take out common G, K and B. So in the numerator we left with Te plus T1, right? And in the denominator, if we again take the common terms, gain of the system, Boltzmann constant and the bandwidth of the operation, we are left again with Te plus T2. So we can write this Y factor Y factor, it is the ratio of, we know the calculated noise powers Pn1 divided by Pn2. This is equal to Te plus T1 divided by Te plus T2. Okay, therefore we can write Y is equal to Te plus T1, okay, divided by Te plus T2. Then we want to write this in terms of Te. That is what we are interested in. Okay, so what we can write then, Yte in plus Yt2 is equal to Te plus T1. Okay, so we'll take out the Te term common on the right hand side. Y into Te minus TE is equal to, we can write T1 minus Y T2. Therefore, from the left hand side, we can take out common TE, which is the internal noise temperature, we can take out TE. So how this can be written? This can be written as, if we take out TE common, I will get Y minus 1 is equal to T1 minus Y T2. Therefore, TE is equal to T1 minus Y T2 divided by Y minus 1. Okay, so here the TE, the internal noise temperature, is given by T1 minus Y T2 divided by Y minus 1. Okay, so what is Y? Where Y is the ratio of Pn1 upon Pn2, where Pn1 and Pn2 are the measured values of noise powers when the device under test is connected to two separate loads which are operating at two different temperatures, T1 and T2. Okay, so this is how we can find out the equivalent noise temperature of the noise generated in the circuit. So here the device under test whose noise we want to determine, this noise is successfully quantified in the form of noise temperature. And this noise temperature is given with this particular equation. TE is equal to T1 minus Y T2 divided by Y minus 1, where T1 and T2 are the temperatures of two different loads and Y is the ratio of noise power measured when these two separate loads are connected to the device under test. Okay, so I hope you understood how to calculate the noise in terms of a noise temperature, and the same procedure we have seen over here. And this particular method sometimes also called as a noise calculation by Y factor method. Okay, so the same we discussed over here, microwave noise measurement. Okay, I hope you understood today's session on the discussion on the measurement of antenna gain and measurement of microwave noise. Okay, and with these two last topics in the module number 5, I declare that module number 5 is fully completed. Okay, as we have gone through, there we saw the total different 9 microwave parameters. We have established a theoretical way to measurement process. Okay, so we started with a VSWR. We measured the unknown frequency, we measured the different types of losses, we measured the attenuation, we measured the dielectric constant, we measured the quality factor, and today we saw the measurement procedure of unknown antenna gain and measurement of noise produced in the microwave circuit. And this will complete module number 5, that is the microwave measurement parameters. Thank you very much.